In the first seminar of this series, we focused on hardware. We looked at data converters, A to Ds and D to As, and how they interface to FPGAs. Then we compared that to the RFSoC. We looked at the technology behind it, chip-level solutions, and then ultimately a small system-on-module built around the RFSoC. The nice thing about the system-on-module is it allows deployment in all different environments and matches the requirements of each one of those. Ultimately, the goal is to go from hardware all the way through development to the quickest path to a deployed solution. For this seminar, I'd like to focus on IP development, the software and the tools and the path you take to create IP and your application in the RFSoC environment. So getting started, I mentioned earlier that the Pentec products are available in all different form factors. For the next two examples, I'd like to use the 3U VPX as our development environment. All Pentec boards shipped with pre-installed IP. What that means is when the board boots up, the FPGA loads from the flash with a full suite of functions ready to go. For the A to D in this case, we have a data acquisition engine. We also have a dual 100 GigE optical interface to stream data off the board. In the DAC direction, we have waveform generators, a test signal generator, and a chirp generator, so you could immediately start sending data out through the DAC. Now, these are both very simple drawings, kind of representing what's inside the board, but this is a more detailed drawing. There's support for the D to A's on the board, as well as the A to D's, and there's actually 8 pairs of these IP sets on the board for all 8 channels. There's our 100 GigE interface. There's support for the ARM processor, and then also our PCIe interface. And all of the blue blocks you're seeing here are IP created by Pentec and installed in the board for immediate use when you power up. So let's take a look at what this setup looks like and how you could start using this IP. So this is the basic configuration for doing development and debugging in 3U VPX. This is a Pentec 3U VPX chassis. If you have your own, you can use that, but this is a low-cost chassis that pretty much just provides power and cooling. In the front is the 5950 Quartz board. You can kind of see all of the analog in and out, plus an antenna connector for GPS, as well as a JTAG connector. In the back is the rear transition module, and there's a number of different connections here for moving data and also for debugging. In this case, we're just going to use Ethernet. So the Ethernet connection is running right back to this PC. And this is pretty much the whole configuration. For the next two examples, I don't even have the Pentec Navigator board support package or FPGA development kit installed because we don't need it for the next two examples I'm about to show. This first example is called Show Info. It's just a very simple example, but it shows you that you can start using the board right out of the box. When the board powers up, the processor boots and it goes out to the flash and grabs the FPGA image. It loads that, and then all the IP we just discussed is available inside the FPGA. Then it goes out to the SD card and grabs the Linux kernel and runs that. Now once Linux is running, I can use any terminal program on my PC to access the ARM processors. Earlier I set my IP address on the processor system to 2, so I set that here. And then I can go in and I'll log in with username root and password root. And now what I'm looking at is the ARM processor running on the RFSoC. So if I look around in there, I see there's 2 directories. There's one called 5950_2.0 that has examples and utilities, and the actual BSP is the BSP_Quartz. I want to go to the examples, so I'm going to go to 5950_2 and the example directory. The examples here are all targeted towards the ARM processor, so that's why it's AArch64. I have another installation where I have it installed on the host, and that will be an x86. So now if I go into that directory, I see a series of folders under there. And these are the example folders. So I have one called Acquire, which are examples that deal with the A to D and capturing data. The next one I have there is Acquire_Ethernet. That sends A to D data out through the 100 GigE interfaces. The next example folder is DACquire. DACquire has examples that deal with the D to A and also acquiring data. I have another folder for the command server, and then I have something called Show Info, and for this example I want to go into Show Info. So let's go into Show Info now, and there's the out file, so let's run that. And as soon as I run that, what's going to happen is it's going to go into the ARM processor, and it's going to grab the data that's stored in the board for all of the board configuration and also do some monitoring. So let's take a look at the top. It's telling me the board is a 6001, which is the SOM sitting on this 3U VPX. It's telling me the Vivado version I used, the revision of this code, the date code, and what the target is, which in this case is a ZU27. I also have temperature monitoring, which is giving me feedback from a number of sensors on the board, plus voltage monitoring, current monitoring. These are all being done live. It gives me the status of another programmable feature on the board, which is the CPLD, and the revision of that. This board can be equipped with optical interfaces. They're not installed on this particular board, so they're showing up as not present. And the 100 gig E uses those optical interfaces, so it's telling me that it can't access those because they're not there. So this is a pretty simple example, but it's a good one because it shows the board could start running right out of the box, and actually it's useful for seeing things like what revision of Vivado is used and what the target is. Now let's take a look at a more sophisticated example. Okay, for this example, let's go back to the block diagram. Now everything I'm showing is built-in IP, so what we're going to do is use the chirp generator that's built in. It'll generate a chirp, send it out the DAC. We're going to wire this back into one of the A to D channels where it'll be acquired, and then ultimately it'll appear on the ARM processor where it can be sent out through the 1 gig E to the host computer for displaying the signal. We need to send the output from one DAC channel into the input of another A to D channel. So I just have this loopback cable. I'll plug it into channel 1's DAC output. It could be any channel, I just chose one. And then we'll plug the other end into the A to D input. And that way now we're sending the DAC output from channel 1 back into the A to D input of channel 1. Let's take a look at the software. Okay, so let's go back to the PC and the terminal program. Again, we're looking at the ARM processor, the Linux prompt. We were in the show info directory. I want to back out to the other examples. And the example we're interested here is DAC acquire. So if we go into that directory, we'll see what's included in there. And there's a handful of different examples, all with different functions. There's a loopback example you can see at the bottom. The one we're going to use is the chirp example. So it's going to actually use the chirp generator, as I said before, and loopback. Now, all of these examples use .ini files. So let's take a look at the .ini file for this particular one, the default file, and see what's contained in there. And again, with the INI files, you can easily change the configuration of any one of these examples. Just change the parameters in there. So let's scroll up to the top. Now, everything is fully documented with inline comments and also with the manual for this example. But a couple things we could see, we're looking at the 5950 as the board. There are channel masks for all the channels, meaning I can turn on or off any of the A to Ds or D to As. I'm using all 8. I have them all turned on. I'm only using channel 1. Let's see. Let's go down a little further and see some of the other parameters that are relevant. Triggering, that's a good one. So if we go down a little bit further, the acquisition can be triggered from a front panel signal or directly from the software like I'm doing here. So just a register write turns on and off the acquisition. I'm using a digital down converter on the A to D, and the center frequency of that is tuned right here. I have them all tuned to the same. They can be different. I have 1.01 gigahertz as the center frequency of the digital down converter. And of course, the chirp itself. It has a starting frequency of 225 megahertz and an ending frequency of 275 megahertz. And if we go down a little further, I think that's probably all the relevant stuff. Let's just run it and see what it looks like. So if I go in here and I run my DAC acquire example, and again, it's going to pull the INI file for all the parameters. It should start configuring and showing me what's happening. Okay, so it's telling me what's being set up on the board. The next thing it'll tell me is how many channels are actually turned on. Again, I have 8 and 8. And the next thing it's going to do is it's going to tell me that it wants me to start the signal viewer. Now, the application itself is running on the ARM processor, but the signal viewer is a host application that I loaded previous to this, and it comes with the BSP. It's just really a self-contained executable that grabs data from the 1 gig E and displays it. So let's go back here, and again, it's included in the BSP. So let's go back to where the BSP was loaded on the host. And I'm going to start the viewer right here. And the parameters I'm going to pass to it are defined right there on the screen on the left. But basically, I'm going to start viewer. The first parameter is the target address. Now, that's a generic name, ZU2760001_3. But I know what the address is from the prior example. It's 192.168.200.2. And the next two parameters are unique port numbers for both client and server. And that pretty much identifies the board, and we can start this running with the right parameters, if I could type them in. And once it starts up, we'll see the signal coming in. So again, the DAC is outputting that chirp, and what we're seeing on the screen here is what the A to D is acquiring, both in the time domain and then in the spectrum analyzer. We can see the chirp. Its center frequency is at 1.01 gig, which I showed before was the tuning frequency, and happens to be the frequency of where this is being down converted. And again, this is a simple example, but everything you're seeing here is running right out of the box. So this was included in the examples on the board. And effectively, all I really needed to do in this case is just install that viewer and start it up and start running it. But there are plenty of times where you will want to go in and you'll want to either create your own IP or modify the IP on the board. So that's the next thing I want to show you. The two main tools from Xilinx for doing IP and software development are Vivado and Vitis. And the way these map into the FPGA resources is Vivado is responsible for creating all the IP that goes into the programmable logic. Vitis is used for creating the software and for working with the operating system. And these two work together to create your application. These you need to purchase directly from Xilinx. Now, the way Pentec maps into the tools is with the Navigator Design Suite. All the IP I showed you before is contained in the Navigator Design Suite. And there's two components. The first maps into Vivado. So it's the Navigator FPGA Design Kit. It contains all of the IP plus additional cores, all the documentation, all the tools you need to work within Vivado and create IP. On the software side is the Pentec board support package, and this contains all the C-callable libraries that are used to access all that IP you've put inside the FPGA. So these are the two tools that allow you to go in and create your own IP. Now for this example, I'm going to go back to this diagram. This actually is the PCIe version of the board, a little bit different from the previous one. This is the model 7050. But what I want to do in here is I want to change the IP that's in there. So right where I have the pointer, there is a traffic meter, and it allows me to monitor how much data is going into the PCIe core based in gigabytes per second. But in this application, I've decided I want to modify it and add another traffic meter right here. And what this will allow me to do is monitor the traffic on a single channel. And I want to compare the single channel traffic with the PCIe traffic and see if there's any gaps in there or if there's any problem. So the way that I do this is I first go in to the FPGA design, I modify that, and then I go into the software and I modify that to control the new IP core that I've added to the FPGA design. So let's take a look at that. The first thing we want to do is open that default Navigator IP block diagram in Vivado. I made a copy called Demo, and we're going to work with that one. So let's click on that, and that'll open up Vivado. So I should probably explain here that I recorded the screen capture earlier, and I'm talking over it now. And rather than watch everything load and take a long time, I'm going to speed up the video in a lot of these segments so we can get through it quicker. So this is the top level of the block diagram. This is the IP that's pre-installed in the board when you receive it. We're going to look specifically at the data acquisition of the ADC data block, and that's what we're going to open up right now. And the way this is built is there are two acquisition blocks, one for channels 0 through 3 and one for channels 4 through 7. So we want to put that traffic meter on channel 0. So we're going to look at the 0 through 3 block and open that up. Now a good place to insert that traffic meter is right after the trigger acquire block. That's where the data is being gated on and off, and that's a place we want to see what that data flow looks like. So we're going to insert it right there. Now all the cores in the Xilinx library and the Pentec library are Axie4 based, so they have consistent signals going in and out, which makes it a lot easier to create IP that works together, but you still want to make sure that the individual parameters on those signals are consistent when you include the new block. So we just want to go through and we want to take a look at the bit widths and some of the various parameters for these, and we're going to copy those into the new block and make sure they match. So now we want to actually import that traffic meter block. The way we set up the Pentec Navigator FPGA design kit is when you install it, all of the IP appears in the pull-down window in IP Integrator. So it's very easy to find all of our IP. There's presently over 150 different blocks. They're easy to find because they all start with the letters PX. So if you just do a search for PX, you can go in and quickly find the core you're looking for and then just pull it into your block diagram. So as I mentioned earlier, you do need to go into the new block and configure the parameters to match the blocks that you're connecting to before and after this block. Now, one very nice feature of the Pentec Navigator FPGA design kit is that every one of those 150 cores are completely documented with a core manual. And these core manuals go into the details of all the things you need to use the core. One of the first things they explain is the theory of operation on how the core works. There's a full functional description. Every register in the core is fully described. And the configuration of the IP parameters that we just set is also described in here. So we want to insert the traffic meter right here. So first we need to delete the existing connection and then connect the traffic meter in between those 2 points. We also need to connect a number of other signals like the clock and the reset. This is described in the manual. We also need to create a control register connection so that we can access this new core from outside the FPGA fabric. And again, this is described in the manual. So because our new core can be accessed from outside the FPGA fabric, we need to give it an address so it can be seen. And it actually can be accessed from 2 different places. It can be seen from the PCIe interface on the board, and that requires an address. And it also can be seen from the ARM processor running inside the FPGA, and it needs an address for that. The way we do that is we go into the address editor, and we find it, and we assign it an address in that tool. So now we've finished adding our new core to the block diagram, and the last step here is to validate the design. So we click that off in Vivado, and we go for a cup of coffee and come back a little while later. Once the design is validated, we need to synthesize, implement, and then generate the bit stream. And I'm going to jump through this pretty quick because all of these are pretty mechanical steps that Vivado will do for you. I will pause here for 1 second though and show you that I'm choosing 2 different strategies. These typically from experience tend to produce a good route, so between the 2 of them I expect at least 1 good timing score. And with that we launch the synthesis in place and route, and that will take a while, so we'll speed that up and come back. Now that we've successfully created the bit stream, we're going to save that off as an XSA file, and that'll contain the bit stream as well as all the hooks the software needs to complete the project. The name of the file we'll save is p6001_3_demo, and that XSA file is what we'll bring into the software tools. So now let's take a look at the path through the tool chain. Up to this point, we've been using Xilinx's Vivado, and remember that the Navigator FPGA design kit works within Vivado. So we took the default image that's in the board, the 7050, and we decided to add an additional IP core, this traffic meter, and this allows us to monitor the data throughput through a specific part of the architecture. We did place and route, we generated the bit file, and ultimately we came out with this XSA file, p6001_3_demo. Now that not only contains the image, the FPGA image that we're going to load into the FPGA, but all the hooks we need to do the next step in software. Now we need to work with Vitis, and remember that the Pentec board support package works within Vitis. So we take the XSA file, bring it in, We're going to generate a new Petalinux kernel, and then we're going to go into the actual application. We're going to take one of the applications that came with the BSP. We're going to modify it so now we can monitor that extra traffic meter, and then we'll run the example. While I showed a lot of the steps in Vivado, I'm going to go a little quicker through the software part of the project. The reason is that the Navigator board support package has a very complete tutorial on creating the kernel and also modifying applications, the exact stuff we're doing right now. And while there are specific details about the Pentec hardware in this documentation, the steps described in this tutorial are the same steps you would take working with any RF SoC chip on any platform. So first we need to create the kernel and the boot images. Now we have this new IP design called P6001_3_demo XSA that came out of the Vivado tools. We also have included in the Pentec BSP templates for all the different hardware configurations. So bringing in the XSA file and bringing in the BSP specific to the board we're using, and I think I mentioned earlier that we're doing this on the Pentec 7050 with the ZU27. We're going to create the new project, configure the kernel components, and then build the kernel and the boot images. And Xilinx provides Petalinux, which is built on Yoctos to build your system images for the RF SoC. What you end up with is the kernel and a lot of boot images as well as a lot of other files that are going to be needed. But you bring those in and package those, and you end up with these three files. The first is the actual bootloader and the system image. That's the image that is the FPGA IP that's going to get loaded into the board. The next one is the Linux kernel, and the next one is the Linux root file system. And the way this maps into the hardware is the boot.bin, the bootloader and the system image gets loaded into the flash. That's the first thing that boots when the board powers up. And then the Linux kernel and the Linux root file system are both copied into the SD card. And that takes care of creating the kernel and the boot images. The next step is to go in and modify the C language application. First, you need to retarget the Navigator BSP to the new project, and this will allow you to output the shared libraries. Again, I'm going through this quickly because the steps are all very well defined in that tutorial in the BSP manual. Next, we need to create the actual application. Now, in this case, we're going to be starting with an example from Pentec, which is in the BSP called acquire.c, and it's a program that allows you to start sampling data on any or all of the A to D channels and send them over PCIe. So we're going to start with that and modify it. So I'd like to show the actual code in Eclipse and point out a few things. So if you remember, we added a core to the design called AXI Traffic Meter, and this came from our Navigator FPGA design kit. In that kit, there are about 150 different cores, and in addition to each core having full documentation and test benches, on the software side, every one of these cores has a matching C library. So if we scroll down here, where is it? We can get to the traffic meter, right? It was right here a minute ago. Where is it? Okay, right there is the traffic meter. So that's the C callable library that controls the IP core we just put in. So now if we go in and add all the hooks we need to access the core and put a printf, or a few actually in there, but one at the end to output the data rate, we can go in and see what it looks like when it's running. I'd like to highlight two of the arguments. The first is ADC frequency. The A to Ds are running at 500 megahertz, and the second is the channel mask. We have it set to 1, so only the 0 channel is actually producing data. So let's take a look at what this looks like when we run it. Okay, so we see the status coming up. We have one A to D running, one D to A, but we're not really looking at the D to A. And then at the bottom we see the traffic meters. So the PCIe DMA traffic meter is seeing 1.128 gigabytes per second of data, and the channel 1 meter, I've been calling it 0, but the software calls it channel 1, is showing 1 gigabyte per second. Now that's what you'd expect, because again, before I mentioned that the A to D is running at 500 megahertz, the data gets padded out to 16 bits or 2 bytes, so you end up with 1 gigabyte per second. This time I'm going to change the channel mask to F. So we're going to turn on 1 through 4 channel. So you can see right now that the A to Ds, 4 of them are actually now sending out data. And now you can see that's a little different. I'm still monitoring, if you go down to the bottom, channel 1 is running 1 gigabytes per second as you'd expect. But now I'm seeing on the PCIe 4.511 gigabytes per second. And that makes sense again because you have 4 channels going in there. There's some overhead to PCIe. So with the overhead, without it, it'd be 4 gigabytes per second. With the overhead, you're about 4.5 gigabytes per second. So again, you're seeing the results you expect. This is just a good example of how you go in, take an existing design, modify it, and all the way through to creating the software to control it. So the last thing I'd like to do is show where the actual code is running in each one of these examples. The first 2 examples were run on our 3U VPX card. This is a graphic representation of the board. When the board powers up and the arms come up, the first thing they do is load the FPGA image, and then they load Petalinux. This board has a PCIe interface, but we didn't use it in the example. We just used the 1 gig E connection to go to a PC. With Petalinux running on the ARM processor, we could just go in with a terminal program and access it. And we actually started the execution of the application on the ARM processor. So it's running under Petalinux on the processor. And that's the point here. Even though the signal viewer was running on the host, the actual application is running locally on that processor. In the example where we were modifying the code, we were running that on our PCIe version of the board. Graphically, it's similar to the other board. It does have a 1 gig E interface on the front panel, but we weren't using that. We actually were using the PCI interface on the board, and the card was actually plugged right into the desktop computer. The difference here is that when the board boots up, not only does the ARM processor load the FPGA image and start up Petalinux, but it starts running the Navigator command processor. The Navigator command processor is a small self-contained application that accepts API commands from either the Ethernet or the PCIe interface, and it's a set of predefined API calls that are supported in our BSP. Now, it's a subtle difference, but when we compile that example, we targeted the x86 so it could run on the PC. And the whole idea here is using the API allows you to program at a higher level, which simplifies the programming task. For a lot of applications, just working at the API level is sufficient. And also, if you want to modify the API, we provide the source for that as well as the command processor application, and that can be modified. So this is just a short list of some of the API commands. The full listing is in the BSP manual. The API is also ideal for our small form factor rugged box. This has a 1 gig E interface on the front. It also has dual 100 gig E interfaces over optical. And when this boots similar to the PCIe version, the ARM comes up, it loads the image, it loads Petalinux, and it starts running the Navigator command processor. Now in this case, again, connecting it through the 1 gig E allows you to control and command it from a PC. Now very often this box will be deployed in a remote location, either on the mast of a ship or maybe in the fuselage of an airplane. So having that remote access through the API is really convenient, as well as being able to stream the high-speed data over the optical interfaces to some other, processing engine or some recording system somewhere else on the ship. So getting back to the topic of this presentation, leveraging software and IP, one of the things that I talked about in the previous presentation, but I touched on here, is the fact that all these different platforms are based on the same architecture. And that's convenient for a few reasons. One is that many customers will develop on the PCI version of the board. It's much more convenient to do it on a desktop, but then take all that IP and software and bring it over to a deployed platform like 3U VPX with a small form factor. Also, we have customers who are switching platforms. They'll develop on one, they'll prototype it, they may actually deploy it, and then eventually they move to a different platform because it's an application that's similar, but it has different environmental requirements. So again, being able to move that IP over is one way to leverage your software. Another way to speed up development is to use the Navigator IP core library. So these are cores that have been tested, they're fully documented. You can pull them right into the IP design with IP Integrator, and very often you'll find IP blocks in there that are either exactly what you need or can be modified to actually give you the function that you need. Building on the included examples that are in the Navigator BSP is another way to get up and running quicker, and very often you can use that as the basis of your application. What we did with the Acquire.c is we added that traffic meter, but that could have been easily something like specific processing or an application-specific function. And using the Navigator command processor is another way to get up and running quickly and also speed your application development. Very often the API interface is a quicker way for you to create your application. So I think that was my last slide. I welcome you to visit www.pentech.com. We have a lot of information up there, plus the manuals are available for most of what I showed you today.